When you look up at the moon on a clear night, it seems still, perfectly suspended in space, glowing softly against the black. It feels distant, almost untouchable, yet that quiet light is part of a constant motion, a pull and stretch that never stops. The moon is moving the oceans beneath your feet right now. Most of the time, gravity feels simple. You drop something and it falls. You jump and you come back down. The Earth's pull gives us weight, keeps the air close, and shapes every moment of our lives. But the deeper you look, the stranger gravity becomes. It doesn't only pull you down, sometimes it stretches, sometimes it lifts, and sometimes it tears worlds apart. If you were floating above Earth, looking down, you'd see a thin blue shell of ocean that seems calm from a distance. But that layer is constantly moving, bulging, and sliding. Twice a day, the sea rises and falls in rhythm with the moon. It's one of the most familiar patterns in nature, yet few people ever stop to think what's behind it. The cause isn't just the moon pulling the ocean up, it's the moon pulling the whole planet in different ways. Gravity gets weaker with distance. The side of Earth facing the moon feels a slightly stronger pull than the far side. It's a tiny difference, just a few micro-Gs. But over an entire planet, that difference becomes a stretch. The oceans bulge out toward the moon on one side and slightly outward on the opposite side. The planet itself is squeezed in the middle. That's why there are 2 high tides every day, not 1. You might imagine the water being sucked toward the moon, but that's not quite right. The moon doesn't only pull the oceans, it pulls the entire Earth. The solid ground moves too by about 30 centimeters. The ocean just flows more easily, so we see the water move. The difference in pull creates 2 bulges that Earth rotates through. That's what we feel as tides. It's an elegant system, a balance of forces that turns the ocean into a slow-breathing surface. Sailors used it for centuries to predict safe passage. Farmers once planted by it. Even in your body, you carry that rhythm, the quiet influence of a nearby world shaping your planet's balance. Now imagine you could freeze time and see those forces drawn out in invisible lines. The moon's gravity would look like threads stretching across the Earth, tugging slightly harder on one side than the other. Those lines are tidal forces. They exist anywhere gravity changes with distance, not only between Earth and the moon, but between every planet and its moons, every star and its planets, every galaxy and its neighbours. These same tidal forces explain why some moons always show the same face to their planet. The constant stretching over billions of years locks their rotation. Our moon used to spin faster, but the Earth's gravity slowed it down until one side always faces us. That's tidal locking, another quiet effect of uneven gravity. But the story doesn't end with gentle tides. The same stretching that lifts our oceans can destroy entire worlds if the distance closes too much. The limit is called the Roche limit, named after the French astronomer Edouard Roche, who calculated the point where a celestial body can no longer hold itself together under the tidal pull of another. Inside this limit, the difference in gravity between near and far sides becomes so strong that it rips the smaller object apart. This isn't theory alone, we can see it in the sky. Saturn's rings are made of icy fragments from a moon that crossed its Roche limit long ago. Jupiter's moon, Io, the most volcanic world in the solar system, is squeezed so intensely by Jupiter's gravity that its surface flexes by hundreds of meters, heating it from within. The same gentle force that moves our seas turns brutal when the distance shrinks. On Earth, we experience only the mild side of this phenomenon. The moon is far enough away, about 384,000 kilometers, that the stretching is subtle. Still, the energy exchange between Earth and Moon is powerful enough to slow Earth's rotation by about 2 milliseconds per century. The lost spin energy pushes the Moon farther away, about 3.8 centimeters every year. If you stood perfectly still on a beach and waited long enough, the tides would change their timing as the Moon drifts away. You can picture the Earth and Moon as 2 dancers bound by an invisible cord. The heavier partner leads, the lighter one follows, but both move. The Moon doesn't orbit a fixed Earth. They orbit a shared point in space, called the barycenter, located about 4,700 kilometers from Earth's center. The pull is mutual. Gravity never acts in one direction only. Every time Earth pulls the Moon pulls Earth back. This is why gravity doesn't always mean down, it means toward. In space, there is no up or down, only attraction between masses. What feels like down to you on Earth is really the direction of the planet's center. If you were standing on the moon, your down would be toward its center. In orbit, where you fall and move forward at the same time, down becomes a circle. This realization, that gravity is both simple and strange, changed our view of the universe. Isaac Newton first explained it as a force acting between masses. Albert Einstein later described it as a curve in space-time, where mass bends the geometry around it. Both views work beautifully to explain tides. Newton's version tells us how strong the pull is. Einstein's version shows why the paths curve and why the stretching occurs at all. You can test a hint of tidal force in your own body. Stand with your feet apart and imagine one foot slightly closer to the moon than the other. The difference in gravity is so small that it's impossible to feel, but it's there, about a trillionth of your weight. It's enough, on planetary scales, to lift oceans. Scientists measure these variations with extraordinary precision. Satellites like GRACE, the Gravity Recovery and Climate Experiment, map Earth's gravitational field by tracking tiny changes in distance between two orbiting spacecraft. When they pass over regions where gravity is slightly stronger, the lead satellite accelerates first, stretching the gap between them. From those tiny shifts, we can detect melting ice sheets, underground water changes, and even shifts from large earthquakes. All of it comes from gravity's uneven pull. The more you look, the less gravity feels like a single force. It's more like a constant conversation between objects. Every star talks to its planets. Every planet whispers back. The moon's message to Earth is subtle but endless. A steady pull, a rhythmic stretch, a silent reminder that even the simplest forces have layers. The next time you stand by the sea and watch the tide slide in, think of that invisible dialogue. The water that touches your feet is answering the moon's call, lifting toward it across an ocean of air and stone. You're part of that movement too. Every atom in your body pulled slightly upward, every moment balanced between Earth's hold and the moon's gentle tug. If you could speed up time, you'd see the moon drifting slowly away from Earth, and the days on our planet growing longer. Each year the moon moves a few centimeters farther out. Over millions of years, that small distance changes the rhythm of the planet itself. When Earth first formed, a day was only about 6 hours long. The moon orbited much closer, and the tides were fierce. Waves surged hundreds of meters high along young shorelines. Gravity was strong, and the pull was violent. Over time, friction between the ocean tides and the seafloor acted like a brake. That friction converted some of Earth's rotational energy into heat and motion, and it transferred part of that energy to the moon. As a result, the moon gained angular momentum and slowly moved outward. The more distant the moon became, the gentler the tides grew and the slower Earth spun. Every second of your life this exchange continues, invisible, constant, unstoppable. You can think of the Earth and Moon as a kind of cosmic balance wheel. One slows, the other drifts. The system preserves its total energy, but the form of that energy changes. It's a dance of motion, gravity, and time. That slowing has left faint marks in ancient rocks. Fossilized coral and sediment layers show rhythmic patterns that record the number of days in a year. Hundreds of millions of years ago, there were about 400 days per year. Not because the year was shorter, but because each day was shorter. The Earth turned faster. The moon's gentle pull stretched those days, one fraction of a second at a time. It's strange to think that gravity, something we can't see or touch, has quietly rewritten the length of a day. Yet this small detail affects everything. The rhythm of tides shapes weather, migration, even biological clocks. Many marine creatures time their life cycles to the moon's phases. Some spawn only during certain tides, when the pull of the moon lifts them closest to the surface. Birds use the tidal cycle to feed. Humans once used it to navigate, measure time, and understand change. Gravity doesn't only move matter, it moves energy through systems that adapt and evolve around its steady pulse. Now look up at the moon again. Its surface tells the story of this long connection. Craters show the scars of impacts from a violent past, but its face is calm now. That calm hides immense internal motion. The moon's interior still flexes slightly under Earth's pull, producing tiny moonquakes. Instruments left by Apollo astronauts recorded them, faint tremors caused by tidal stress. Even across nearly 400,000 kilometers, the Earth's gravity continues to shape the Moon's body. This effect isn't unique to our system. Across the solar system, tidal forces sculpt worlds. The moons of Jupiter show it best. Io is squeezed so much by Jupiter's gravity that its interior melts, feeding over 400 active volcanoes. Europa, slightly farther away, flexes less violently, but enough to keep an ocean of liquid water beneath its icy crust. That hidden sea may be one of the best places to search for life beyond Earth. Farther out, Saturn's moon, Enceladus, shows icy geysers that spray water vapour hundreds of kilometres into space. Those plumes come from tidal heating too. As the Moon moves through Saturn's varying gravitational field, its interior warms, cracks, and releases jets of vapour. Gravity, acting across 1 billion kilometres, creates warmth and motion in frozen worlds. You can trace a direct line from the tides on Earth's beaches to the geysers of Enceladus. The principle is the same, a gradient in gravity stretching one side more than the other, converting motion into energy. This is how the universe reuses its own forces, turning orbital mechanics into heat, structure, and even the potential for life. On Earth, we depend on this equilibrium. The Moon stabilizes the planet's tilt, keeping our climate relatively mild. Without it, Earth's axis would wobble chaotically under the pull of other planets. Seasons would swing wildly. Ice ages and heat waves would come unpredictably. The Moon's steady pull holds the planet upright in a delicate balance. Gravity doesn't only pull downward, it also holds our environment steady enough for life to survive. The Moon's influence reaches even into the smallest rhythms of timekeeping. Before mechanical clocks, people measured time using tides and lunar cycles. Early coastal civilizations noticed the link between the Moon's position and the behavior of the sea. The connection was reliable, measurable, and beautiful. The Moon became humanity's first clock. Today, atomic clocks track time with unimaginable precision, accurate to billionths of a second, but even they must account for the slowing of Earth's rotation caused by tidal friction. Every few years we add a leap second to keep our clocks aligned with the planet's gradual deceleration. A ripple from the ocean floor caused by the Moon's gravity reaches into the code that defines modern time. The connection is both ancient and alive. Imagine standing on a beach billions of years from now. The sun is dimmer. The continents have shifted. The Moon hangs smaller in the sky because it has drifted even farther away. Tides are weaker. Days are longer. Gravity's conversation continues, slower now but still speaking. The same quiet exchange that once pulled molten tides across the early Earth still flows, unchanged in its principle. Gravity isn't only a force, it's a sculptor of history. Every geological record, every orbit, every breath of wind owes something to its invisible shaping. When you think of gravity as always pulling you down, you miss the full story. It also lifts oceans, bends time, stabilizes climates, and guides evolution. Astronomers use the word gradient to describe the difference in gravitational strength across distance. The bigger the gradient, the stronger the tidal force. Near a black hole, that gradient becomes extreme. If a person ever drifted too close, the difference between the pull on their feet and head would stretch them apart, a process colourfully nicknamed spaghettification. It's the same physics as the tides, only magnified to a deadly scale. The same principle that makes a gentle ocean wave can destroy a star. When a star ventures too near a supermassive black hole, the tidal forces can tear it apart completely. Astronomers have watched this happen. A bright flare of light as the star's material spirals inward, shredded by gravity's uneven grip. The universe shows no distinction between beauty and violence in these moments. The same law applies everywhere, from your falling coffee cup to a dying sun. Gravity's story is one of unity. From the Moon's tug on the sea to the tearing of galaxies, it operates with the same rule. Every mass attracts every other. The differences in that attraction shape the structures we see. Mountains, rings, waves, orbits, all are patterns written by this quiet script. When you walk outside at night and feel the pull of your own weight, you're part of that same equation. You're being pulled not only by Earth but by the Moon, the Sun, and every other mass in the cosmos. The combined result feels like down, but the truth is broader. You're falling toward everything, and everything is falling toward you. What keeps the world stable is the balance among those countless pulls. The idea that gravity doesn't always pull you down isn't just poetic, it's literal. Gravity stretches, bends, stabilizes, and sometimes destroys. It turns orbits into warmth, motion into shape, and time into rhythm. The moon reminds us of that every night, rising over the horizon and shifting the tide under its gaze. The story of gravity and the moon is, in the end, the story of motion seeking balance. Every drop of water that rises on the shore, every second added to the length of a day, every faint tremor on the lunar surface, they're all connected in one slow dialogue between two worlds. When you watch the tide turn, you're seeing that conversation made visible. A pull here, a push there, a quiet stretching across a gulf of space, and all of it happening beneath a sky that looks still, but never stops moving. Before science could measure gravity, people watched it. Long before words like force or mass existed, the moon's pattern was already marked in shells, stones, and stories. Ancient coastal people saw the tides move in rhythm with the moon's shape. When the moon grew bright and full, the water rose higher. When it faded to a sliver, the tides softened. To them, this wasn't physics, it was connection. They knew the sky touched the sea, even if they didn't yet know how. For thousands of years, this link guided navigation and survival. Fishermen in the Arabian Gulf and Pacific Islands built calendars that matched lunar phases to the behavior of tides. Early farmers in the Nile Valley watched the moon to predict seasonal floods. Every civilization near the sea learned to read that slow breathing of water. Then came the thinkers who tried to explain it. In the 4th century BCE, Aristotle wrote about the sea's motion, but didn't connect it to the moon. He believed the Earth itself exhaled water like a living organism. It took nearly 2,000 more years before the connection was proven. In the 17th century, Galileo suspected the moon's influence, but proposed that tides came from the Earth's motion around the sun. His reasoning was elegant but incomplete. The true explanation arrived with Isaac Newton. In 1687, his Principia Mathematica laid out the law of universal gravitation. Newton realized that tides must come from differences in the moon's gravitational pull across Earth's diameter. He even calculated how the sun also affects the ocean, sometimes amplifying the moon's effect, sometimes reducing it. When the sun and moon align during full or new moons, we get spring tides with the largest range. When they're at right angles, we get neap tides, the smallest. That pattern has held ever since. Newton's equations described the invisible perfectly. They explained why the oceans bulged on both sides, why there were 2 high tides per day, and why the cycle matched the moon's orbit. For the first time, humanity understood that what happens on a beach is tied directly to celestial geometry. The line between astronomy and daily life disappeared. After Newton, others built tools to measure what he described. By the 18th century, tide gauges appeared in ports around Europe. These mechanical floats and pulleys recorded sea levels on rolls of paper. Over decades, the curves of those recordings matched the predictions from Newton's mathematics almost perfectly. The idea that you could predict a tide years in advance, using only gravity and time, was a revolution. It turned the moon into a clock more precise than any made by human hands. By the 19th century, scientists began to see that the same principle applied everywhere. The pull between bodies wasn't just a curiosity, it was the architecture of the cosmos. William Thomson, later known as Lord Kelvin, built one of the first analog computers to predict tides using a system of pulleys and rotating wheels. His device could forecast the height of the sea at any port, days or months in advance. It worked because gravity is consistent. The same math that governed the moon and ocean could describe any orbit in the universe. Then came Einstein. His general theory of relativity changed the meaning of gravity itself. Instead of being a force acting across space, gravity became the curvature of space and time caused by mass. Objects follow those curves naturally. Tides, in Einstein's picture, come from the way space-time is warped more on one side of the Earth than the other. It's the same outcome, viewed through a deeper lens. Newton told us how gravity works. Einstein began to show us why. Modern instruments have turned those ideas into images. Satellite missions like GRACE and its successor, GRACE Follow-On, orbit Earth in pairs. By measuring the changing distance between them with lasers, they can map gravity variations to the millimeter. The result looks like a living topographic map of invisible forces, a planet breathing under the pull of the moon, the sun, and shifting masses of water and ice. From those measurements, scientists now know that Earth's gravitational field changes over time. As Greenland's ice melts, the mass distribution shifts, altering local gravity. When large earthquakes move rock deep underground, satellites detect the change. Even seasonal rainfall can be seen through its effect on the planet's mass balance. Gravity becomes a messenger, carrying news about the state of the planet itself. We've also learned to apply this knowledge far beyond Earth. By observing the motion of moons and rings around other planets, astronomers can estimate their internal structure. The way a planet's gravity distorts its satellites tells us whether it has a solid core, a thick ocean, or layers of gas. In this way, gravity becomes a probe, silent, precise, and universal. One striking example is Saturn's moon Enceladus. When the Cassini spacecraft flew through its icy plumes, it also measured how Enceladus wobbled under Saturn's pull. The data showed that its crust flexed too much for it to be solid all the way through. There had to be a global ocean beneath the ice. The same tidal stress that lifts our oceans keeps that hidden sea liquid. Without gravity's stretch, Enceladus would be frozen solid and lifeless. Even galaxies follow the pattern. When two galaxies pass near each other, their mutual gravity pulls stars into long tidal tails that arc across space. Those tails are light years long, shaped by the same principle that moves the tide at your feet. The scale is vast, but the rule is identical. Gravity changes with distance, and those changes create motion. It's a remarkable symmetry. The same mathematics that explain the ocean's rise and fall can describe the structure of galaxies. The universe works like a repeating pattern of motion and stretch, scaled up or down across billions of kilometers. When you think about that, the word down loses meaning. On Earth we define down as the direction of gravity's pull, but in the universe, down is everywhere and nowhere. Astronauts in orbit aren't beyond gravity, they're within it. They're falling toward Earth at the same rate the spacecraft moves forward, so they keep missing the ground. Their weightlessness is really continuous falling, a perfect demonstration that gravity doesn't pull down. It pulls inward, equally across the curve of motion. The International Space Station circles Earth every 90 minutes, experiencing tidal forces across its structure. Instruments inside can detect the minute differences in gravity from one end to the other. It's an ongoing lesson that gravity never turns off. Even in the emptiest regions of space, the pull is there, faint but real, shaping every orbit, every path of light. We now simulate these forces with supercomputers. Models can show how stars tear apart under extreme gravity, how planetary systems evolve, and how dark matter bends light. These simulations confirm what ancient observers once sensed by watching the sea. Gravity's reach is subtle but endless. The same moon that guides the tide also teaches us how the universe holds itself together. When you trace this chain of understanding, from shells marked with lunar symbols to satellites mapping gravity's pulse, you see continuity. Humans have always tried to find patterns in motion. The tide was our first classroom, the moon our first teacher. Every new discovery, from Newton to Einstein to Grace, adds another layer to that lesson. Gravity is not a single direction. It's a dialogue between all directions, a negotiation between masses across space. If you could listen to it, gravity would sound like slow music, a note for every orbit, a rhythm for every wave, a hum that connects everything moving, falling, or turning. We don't hear it, but we live inside its song. The moon we see today is calm, but its creation was anything but gentle. More than 4 billion years ago, when Earth was still forming, the planet collided with a Mars-sized body we now call Theia. The impact melted much of Earth's surface and threw a ring of molten debris into orbit. That ring eventually gathered into the moon. From its first moments, our satellite was a child of violence and gravity. At first, the newborn moon orbited close, only about 20,000 kilometers above Earth's surface, less than a tenth of its current distance. The tidal forces then were enormous. Earth's crust flexed and heaved under the moon's pull, releasing heat and shaping the planet's early geology. The young ocean, still steaming from the impact, rose and fell in waves taller than skyscrapers. The tides would have circled the globe every few hours, carving shorelines and stirring minerals in the sea. Those early tides did more than shape rocks. They mixed chemicals. The constant motion between ocean and land may have helped form the first complex molecules that led to life. Modern experiments show that wetting and drying cycles can encourage simple amino acids and sugars to link into chains, the basic components of life's chemistry. The moon's gravity, by moving water across primitive coastlines, could have provided the rhythm needed for those reactions. Life's origin may carry the fingerprint of tidal motion. As the moon moved outward, the tides softened, but their influence endured. Tidal mixing still helps circulate nutrients through the ocean today. It drives currents that feed coral reefs and sustain marine ecosystems. It also plays a quiet role in regulating climate. By stirring the ocean, tides help distribute heat from the equator toward the poles, keeping temperatures more even. Without that constant redistribution, parts of the planet would grow hotter, others colder. Gravity shapes not only the shape of the sea, but its balance. On a deeper level, tides affect the solid Earth as well. The crust rises and falls by centimeters each day as the planet flexes under the moon's pull. Sensitive instruments called gravimeters record these tiny movements. Even underground reservoirs of magma respond. In volcanic regions, tidal stress can subtly change the timing of eruptions. It's not the cause, but it can act as a trigger, the final nudge that releases stored pressure. The link between the moon and volcanic activity is faint but measurable, another reminder that the sky and ground are never fully separate. This connection between tidal forces and energy release appears on other worlds too. Io, the innermost of Jupiter's large moons, is a prime example. Its orbit is slightly stretched by the combined pull of Jupiter and its neighbouring moons Europa and Ganymede. That stretching keeps Io's interior molten. The result is a surface coated with sulfur and dotted with hundreds of volcanoes erupting almost continuously. It's the most geologically active body in the solar system, all because of tides. On Earth, the same mechanism works on a gentler scale. The moon and sun raise ocean tides that contain immense amounts of energy. Engineers have begun to capture some of that power with tidal turbines and barrages. These systems convert the steady motion of the sea into electricity. It's a renewable source, driven by the gravity of nearby worlds. Every rotation of the Earth turns the pull of the moon into usable energy, a direct link between celestial mechanics and human technology. But tidal forces also have limits. Too much stretching can tear things apart. Astronomers see this in the rings of Saturn and Uranus, vast belts of ice and rock that once might have been moons. Those bodies crossed within the Roche limit, where the difference in gravity between their near and far sides exceeded their own cohesion. They disintegrated, spreading into countless fragments. From destruction came beauty, as those fragments flattened into shimmering rings that now circle their planets like frozen tides. The same fate may one day await our moon, though not for billions of years. When the sun becomes a red giant, it will expand and change Earth's orbit. Tidal forces between the bloated sun and the Earth-Moon system could alter the balance, drawing the moon inward again. Whether it will survive or break apart remains uncertain, but the idea illustrates the cycle of gravity's reach: creation, balance, decay, and renewal. For now, our relationship with the moon remains stable. Its pull continues to define Earth's rhythm, not only the physical motion of tides, but also cultural and biological patterns. Human calendars still mark lunar phases. Languages around the world preserve traces of it. The words for month and moon share the same root in dozens of languages. Farmers once planted by its light. Poets measured time by its changes. Gravity connects science, art, and tradition in a single motion. If you stood on the moon and looked back at Earth, you'd see the same effect in reverse. Our planet would dominate the sky, about 4 times larger than the moon appears from here. Its blue and white surface would shimmer as clouds and oceans reflected sunlight. Earth's gravity would raise small tides in the lunar crust, though there's no water to move. The Earth and Moon pull on each other equally. Only the results differ because of size and composition. Even at that distance, you'd see the balance in motion. Earth's oceans swelling under your feet, the Moon's horizon curving gently below you, both parts of the same system. The line between them isn't a boundary, but a connection. A continuous exchange of force. The Moon doesn't orbit a static planet, and Earth doesn't simply hold the Moon. They move together, each shaping the other's path. that shared motion has consequences for time itself. Because of tidal friction, Earth's rotation slows and the moon recedes. Over immense spans, this process changes the length of the day, the number of days in a year, even the shape of the Earth's orbit. The solar system is not a fixed clock, but a fluid structure, always adjusting to the tug of its parts. Astronomers call this tidal evolution. It explains why many moons in the solar system are tidally locked, always showing one face to their parent planet. It's a natural endpoint of the stretching process, when rotation and orbit synchronize. Our moon has reached that state. One hemisphere always faces Earth, frozen in that pose forever. The far side, unseen from our surface for most of history, remained mysterious until the space age revealed it. Gravity sculpted even the way we see the sky. That hidden half of the moon reminds us that gravity doesn't act in isolation. It shapes perception too. The tides we see, the light we measure, the patterns we trust, all come from geometry and distance. When gravity stretches across space, it doesn't only move objects, it moves perspective. Every motion of the moon tells a story of gravity's flexibility. The same force that pulls you down when you drop a stone can, given time and distance, shape oceans, ignite volcanoes, and sustain life. What changes isn't the rule, but the context. The dance between attraction and motion defines everything from the smallest ripple in a tide pool to the broad arcs of planetary rings. The next time you see the tide rise, imagine it in slow motion. Picture the moon above, its invisible pull reaching through thousands of kilometers of rock and water to lift the edge of an ocean. That movement connects you to an ancient rhythm older than mountains, older than life itself. You stand within it, balanced between the downward pull of Earth and the sideways stretch of the moon. For most of history, gravity was invisible and unquestioned. People saw objects fall and assumed it was natural, not something that needed explaining. The idea of down felt absolute. Yet the journey from that simple notion to our current view of gravity is one of science's quiet revolutions, a story that began with a falling apple and ended with the bending of space-time itself. Isaac Newton's insight in the 17th century changed everything. He realized that the same force that pulls an apple toward the ground also keeps the moon in orbit. The moon, he said, is perpetually falling toward Earth, but moving forward fast enough to keep missing it. That single idea unified the heavens and the Earth. For the first time, motion in the sky and motion on the ground obeyed the same law. Newton's law of universal gravitation described gravity as a force between any two masses. It depended on their size and the square of the distance between them. This simple equation could predict the paths of planets, comets, and moons with remarkable accuracy. For 2 centuries, it stood unchallenged. Gravity was the invisible glue that held the cosmos together. But in the early 20th century, Albert Einstein found that the picture wasn't complete. When he developed his general theory of relativity, he replaced the idea of gravity as a pulling force with a new vision. Space and time themselves are flexible. Massive objects warp space-time, and smaller objects move along those curves. What we feel as gravity is really motion through curved geometry. Earth doesn't pull the moon, it bends the space the moon moves through. This new view explained phenomena that Newton's equations couldn't. The orbit of Mercury, which deviated slightly from predictions, matched perfectly when Einstein's corrections were applied. Light too was affected by gravity. During a solar eclipse in 1919, astronomers observed starlight bending around the sun, just as Einstein had predicted. The universe wasn't bound by invisible strings, it was shaped by the fabric of reality itself. From this came a new understanding of tides. They're not just differences in pull, but differences in space-time curvature. The side of Earth closer to the moon sits slightly deeper in the moon's gravitational well than the far side. The result is stretching along the line between them, the same effect Newton described, seen through a new lens. Einstein's equations also predicted something extraordinary. Ripples in the space-time caused by accelerating masses. When massive objects like black holes or neutron stars move rapidly, they send out gravitational waves, faint distortions that travel at the speed of light. For a century, these waves remained hypothetical. Then, in 2015, detectors at the Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded them for the first time. 2 black holes had collided more than 1 billion light-years away, and their merger sent a vibration through space-time that passed through Earth. The signal lasted only a fraction of a second, but it confirmed one of Einstein's most daring ideas. The detection of gravitational waves opened a new way of seeing the universe. Until then, astronomy relied on light, visible, radio, infrared, X-ray. Now we can listen to the universe's structure itself. These waves carry information about events that light can't escape, like black hole collisions. They show that gravity isn't static. It moves, it radiates, it connects the cosmos through motion itself. The understanding of gravity has grown more subtle with each generation. What began as the pull that made things fall became a theory of geometry, then a tool for exploring invisible phenomena. Yet even now, the concept of down remains deeply human. On Earth, we orient ourselves toward the planet's center because that's where gravity points us. But in space, down disappears. Astronauts in orbit experience microgravity because they were in continuous free fall. They haven't escaped gravity, they're immersed in it, moving within its curves. Inside the International Space Station, objects float not because there's no gravity, but because everything, station, astronaut and air, is falling together. The same principle explains why satellites stay in orbit and why planets follow curved paths around stars. Down becomes relative, a direction that depends on where you stand and what mass dominates nearby. Consider the Moon's surface. There, gravity is about 1/6 as strong as Earth's. Walking feels slow and exaggerated. Dust rises higher when you step because it falls more gently. Down still points toward the lunar center, but the sensation is lighter. The Apollo astronauts experienced this directly. Every movement became a slow-motion arc. Their footprints, still preserved, mark the quiet pull of a smaller world. Move farther into the solar system, and gravity continues to shift. On Mars, you'd weigh about 1/3 of your Earth weight. On Jupiter, you'd be crushed before you could stand. Each world defines its own sense of down. In deep space, far from any massive body, the concept loses meaning altogether. There, you're not pulled anywhere in particular. You're between curves in space-time, drifting in a vast equilibrium of attraction. This relativity of direction challenges our instincts. We think of gravity as something that acts on us, but we also act on it. Your body, small as it is, exerts gravity too. Every atom attracts every other atom. The effect is minuscule, but it's there. In principle, two people standing close together pull on each other with an imperceptible force. The entire universe is a web of mutual attraction, every part contributing to the shape of the whole. Einstein's theory also revealed a deeper connection between gravity and time. The stronger the gravitational field, the slower time passes. This isn't a metaphor, it's measurable. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. Near a black hole, the effect becomes extreme. Time can slow to a crawl relative to the outside universe. The same gravity that keeps you on the ground also defines how quickly your moments pass. This link between gravity and time has practical use. The GPS satellites that guide navigation depend on precise timing. Their onboard clocks run faster than those on Earth because they're higher up, where gravity is weaker. Engineers must correct for this difference every day. Without those adjustments, GPS locations would drift by kilometers. A simple act, checking your phone's position, depends on Einstein's equations working quietly behind the scenes. Gravity has grown from an everyday experience into a cosmic principle that ties together motion, time, and space. Yet its essence remains the same: attraction between masses, shaping motion across the universe. Whether you're watching a falling apple or the merger of black holes, you're seeing the same rule expressed at different scales. For all our progress, gravity still holds mysteries. We don't yet know how it fits with quantum mechanics, the theory governing particles and forces at the smallest scales. Physicists suspect that gravity might emerge from deeper principles, perhaps from the structure of space-time itself, or from quantum fields woven together. Experiments continue, using everything from particle colliders to space-based observatories to find the bridge between these two great theories. Some researchers propose that gravity may not be a fundamental force at all, but an effect of entropy, a measure of disorder in the universe. Others search for hidden dimensions or unseen particles that could carry gravitational effects. Whatever the truth, Each discovery brings us closer to understanding why gravity behaves as it does, and why it doesn't always pull down. If you step outside at night and look at the moon, remember that the same gravity shaping its orbit also slows time on your wristwatch, bends light through the atmosphere, and holds your body to the planet. Every heartbeat you feel happens within that same geometry. You're not separate from it. You're part of its curvature, a brief structure in the long fold of space-time. Gravity is both the simplest and most profound feature of the universe. It keeps your feet on the ground and holds galaxies together. It defines direction, rhythm, and time. And sometimes, when the forces align just right, it reminds us that down is only one way to describe the endless pull between everything that exists. Every launch from Earth begins with a fight against gravity. Rockets rise not by escaping it, but by outrunning the pull long enough to enter free fall around the planet. In orbit, they're still under gravity's influence completely, but they move fast enough that the ground curves away beneath them. This is the essence of flight in space, not defying gravity but cooperating with it. Each maneuver astronauts make depends on precise calculations of gravitational force. Even tiny errors can shift a spacecraft's path by thousands of kilometers. Engineers use these calculations to design gravity assists, using the pull of planets to accelerate or redirect probes without burning extra fuel. A spacecraft approaching Jupiter, for example, can swing around it and steal a fraction of its orbital momentum, gaining speed for free. Gravity becomes a highway rather than an obstacle. This technique has taken our machines to the edges of the solar system. The Voyager probes, launched in the late 1970s, used a rare alignment of planets to visit Jupiter, Saturn, Uranus, and Neptune in one continuous journey. Each encounter bent their paths outward, flinging them faster and farther. Today, Voyager 1 has left the solar system entirely. It moves through interstellar space at more than 60,000 kilometers per hour, still guided by the same laws that drop an apple to the ground. Gravity assists remain central to mission design. The Cassini probe used them to reach Saturn, weaving between Venus, Earth, and Jupiter to build speed. The Parker, solar probe, now studying the Sun, loops past Venus repeatedly to adjust its orbit, each time falling closer to the Sun than any spacecraft before it. Even when we travel by machine, we ride on gravity's curves. As we return to the Moon and plan missions to Mars, gravity again defines what's possible. Launching from Earth requires immense energy because the planet's gravity is strong. Launching from the Moon will be easier. That difference means future spacecraft could be built or refueled in lunar orbit, taking advantage of the Moon's weaker pull. In time, we might use the Moon as a stepping stone, a natural platform between Earth and deeper space. Understanding gravity also shapes where and how we might live beyond Earth. On Mars, where gravity is about 1/3 of Earth's, long-term habitation could affect human health. Muscles and bones weaken when not constantly loaded by gravity. Astronauts aboard the International Space Station already face this problem. They exercise for hours each day to slow bone loss and maintain strength. On Mars, future settlers will need new ways to adapt. Artificial gravity, created by rotating habitats, is one possible solution. Spin a large structure fast enough, and centrifugal force can mimic the pull of gravity along its inner walls. These concepts, once imagined only in science fiction, are now serious engineering studies. The design of rotating habitats, lunar bases, and orbital stations all comes back to one question: how much gravity do humans need to stay healthy? The answer is still uncertain. Experiments in partial gravity are rare, but upcoming missions to the Moon and Mars will begin to reveal how our bodies adjust when down feels different. Gravity also shapes our sense of orientation and motion. On Earth, our inner ears and muscles rely on a constant pull to tell us which way is up. In microgravity, that reference disappears. Astronauts often feel disoriented when they first arrive in orbit. Their brains must recalibrate to a world where any direction can be down, depending on perspective. Over time, they adapt, learning to move and work in 3 dimensions without a fixed vertical. It's a subtle lesson in how deeply gravity defines our perception of reality. Future missions will push these adaptations further. As humanity ventures toward asteroids or Mars, travelers will experience varying gravity levels, from microgravity in transit to partial gravity on the surface. Each transition will challenge the body and mind. Engineers are already designing spacesuits, tools, and vehicles to work under changing gravitational loads. The success of those designs will determine whether life beyond Earth becomes sustainable. The Moon offers a perfect testing ground. Its weak gravity makes it ideal for studying how humans function outside Earth's constant pull. Lunar dust and terrain present hazards, but the low-weight environment also allows heavy structures to be built. With less material, bases could be buried beneath regolith to shield from radiation. Greenhouses could use low pressure and controlled light. Gravity defines every design choice, from airlocks to sleeping quarters. As exploration expands, gravity also becomes a communication tool. The study of gravitational waves has already revealed mergers of black holes and neutron stars. In the future, space-based detectors like LISA, the Laser Interferometer Space Antenna, will orbit the Sun, listening to lower frequency waves that ground observatories can't detect. These instruments will map the invisible structure of the universe, showing how gravity moves across billions of light years. It's a new form of astronomy, one that doesn't rely on light at all. Gravity also serves navigation. Deep space missions use the predictable patterns of gravitational fields to orient themselves. By measuring how signals from known pulsars or planetary bodies shift under gravitational influence, spacecraft can determine their position with extreme precision. It's the celestial equivalent of GPS, guided not by satellites, but by the steady geometry of space itself. One of the most intriguing frontiers in gravitational research is propulsion. Concepts like the gravity slingshot are already routine, but more speculative ideas explore how gravitational fields might one day be manipulated. Though still theoretical, researchers study how exotic forms of matter or energy could warp space-time locally, creating controlled curvature. If such manipulation ever becomes practical, it could change travel forever, bending the geometry of space rather than crossing it. For now, the most realistic path forward is to keep working with gravity, not against it. Every orbit, landing and ascent depends on understanding its behavior. The more precisely we can model gravity, the farther we can go. From satellites monitoring climate to probes exploring icy moons, success depends on predicting the smallest variations in gravitational pull. Our awareness of gravity's reach also deepens our sense of place. Every mission outward reveals that space is not empty. It's filled with structure shaped by mass and time. The same rules that govern the moon's tides define the orbits of exoplanets, the shapes of galaxies, and the dance of dark matter. The universe is an ocean of curvature, and we are learning to sail upon it. Human exploration will always be a story of balance between motion and pull. Gravity binds us, but it also guides us. It tells us where the stable points are, the orbits, the paths of least resistance, the routes that conserve energy. When astronauts speak of insertion burns or transfer windows, they're describing moments when Earth's pull, the Moon's pull, and the motion of the spacecraft align perfectly. Every successful journey is a negotiation between competing gravities. In the quiet vacuum of space, you might think gravity fades, but it never ends. It links every planet, moon, and asteroid in a continuous web. When a spacecraft passes one world, it feels the faint tug of the next. Navigation through that web is an art learned from centuries of watching tides rise and fall. The same principle that moved the ancient seas now guides ships among the stars. When the first humans return to the moon and look back at Earth, they'll see the planet shining against black space. A blue world held together by gravity. The pull that once seemed so limiting will have become a bridge between worlds. The same force that kept us grounded will have carried us outward. Gravity began shaping you long before you were born. Every cell in your body grew and organized under its pull. The way blood flows, the way your muscles anchor to bone, the way your balance adjusts with every step, all evolved to cooperate with Earth's gravity. Remove that constant and everything changes. Astronauts who spend months in orbit return taller than when they left. Without gravity compressing the spine, the vertebrae separate slightly. Their hearts shift upward. Their faces swell as fluids redistribute through the body. Even taste and smell can change. The human form is tuned for gravity's direction and strength. Change either, and the body must learn again how to be itself. On Earth, we almost never notice this adaptation. Gravity is so constant that it disappears into the background of experience. You don't wake up each morning grateful for the pull that keeps your coffee in its cup and your feet on the ground. Yet without it, everything familiar would unravel. The atmosphere would drift away, the oceans would float off into space, even time itself would tick differently. In that way, gravity is both invisible and intimate. It connects the most personal moments, walking, sleeping, breathing, with the grandest structures in the cosmos. The same curvature that holds you to the planet holds galaxies together. It's a link between scales, a reminder that complexity grows from simple laws repeated endlessly. Our ancestors sensed this unity, even if they couldn't describe it. They looked at the moon's pull on the sea and felt that it mirrored something within themselves, a rhythm that matched heartbeat and tide. Rituals, calendars, and myths emerged from that pattern. The moon became a symbol of constancy and change, both bound by gravity's rhythm. Even today, the language of cycles and balance traces back to that ancient observation of the tides. Science has since replaced myth, but the sense of connection remains. When you watch a tide roll in, you witness a process that began billions of years ago and will continue long after humanity's gone. That movement ties you to the birth of the moon, the evolution of oceans, and the slow expansion of time itself. You stand in the middle of an unbroken story written by gravity's hand. Life adapts to this pull in countless ways. Plants grow upward, sensing gravity through specialized cells that guide their stems and roots. Some deep-sea creatures rise and fall with tidal currents, living in synchrony with the moon's motion. Migrating animals navigate by gravitational cues as subtle as the tilt of the Earth. Even in the smallest behaviors, the influence of gravity shapes survival. Human culture reflects it too. Our architecture, art, and even our imagination depend on the idea of up and down. Towers symbolize ambition because they rise against gravity. Bridges express mastery because they span across it. Every structure we build negotiates with the same pull that shapes mountains and valleys. Engineering is, at its core, an argument with gravity, one we never truly win, only balance. When you think about it, the notion of down is one of humanity's oldest metaphors. It represents weight, effort, and sometimes despair. Lifting up means hope, falling means failure. We use gravity's language to describe emotion and meaning. The physical and the poetic mirror each other because both grow from the same experience, living under a constant pull. Yet gravity also gives comfort. It grounds us, literally and figuratively. When you lie down to sleep, you surrender to its hold, letting the earth cradle your weight. That quiet pressure signals safety and rest. In a sense, gravity is the body's reminder that you belong here, part of a planet large enough to carry you. This sense of belonging extends far beyond Earth. The laws of gravity link us to everything else in the universe. The stars you see at night are organized by it, spinning in patterns that echo the motions of the sea. Galaxies form filaments and clusters shaped by the same attraction that draws a pebble to the ground. Dark matter, invisible yet massive, threads through those structures, amplifying gravity's influence. Without it, the universe would be a thin mist of particles drifting apart. Gravity gives it shape, depth, and time. In that way, gravity is the architect of structure. It turns chaos into form. It collects gas into stars, stars into galaxies, galaxies into clusters. It's not just a pull, it's a sculptor of order from randomness. Each star that shines does so because gravity compressed its matter until fusion ignited. Every orbit, from electron to planet, follows the logic of attraction and balance. This universal pull also defines the edges of what we can know. Black holes, the densest objects in existence, represent gravity's extreme. Their fields are so strong that nothing, not even light, can escape. Yet even they follow the same equations that describe the tides. The difference is scale, not kind. In that sense, a black hole is a cosmic tide pulled to infinity. Astronomers studying these objects now use gravitational waves to listen to their collisions. The data reveal masses, spins, and distances, all encoded in ripples of space-time. From such measurements, we're learning how galaxies evolve, how stars die, and how the universe itself grew from its first moments. The quiet tug that once moved the sea has become a tool for decoding the cosmos. Gravity's influence even touches philosophy. It challenges the idea of separation. Nothing in the universe is entirely isolated, everything interacts through this field. Even when we think of being alone, we're physically connected to every atom of mass around us. The smallest stone underfoot and the most distant quasar share a measurable link, however faint. The universe isn't a collection of independent objects, it's a web of attraction, each part shaping the rest. Understanding this doesn't make gravity less mysterious. If anything, it deepens the sense of wonder. The more precisely we describe it, the more profound it becomes. We can write its equations and measure its effects to astonishing accuracy, yet we still can't explain why space-time curves at all. Gravity remains the quiet mystery at the heart of everything, simple in behaviour, infinite in consequence. Perhaps that's why it resonates so strongly with human thought. It reflects our own desire for connection, to pull toward others, to find balance, to orbit around meaning. These are echoes of the same principle that guides planets. When you feel drawn to someone or something, you're enacting a metaphor written by the universe itself. The moon's pull on the sea, Earth's pull on the moon, the sun's pull on both. All are variations of one relationship repeated at different scales, and you, standing beneath the same sky, are part of it. You're not outside the system observing it, you're within it, moving in harmony with every mass that exists. Next time you look up and see the moon, try to feel the connection rather than simply notice it. The faint upward pull you can't sense is real. It's lifting oceans, bending air, and stretching the crust beneath you. You and the water, the rocks, and the light are all responding to the same silent command. Gravity doesn't ask permission. It simply acts, weaving motion into unity. The story of gravity isn't only about the cosmos, it's about continuity, how every movement, from the fall of a raindrop to the drift of galaxies, follows the same rule. That realization carries humility. The laws that shape stars also shape you. To understand gravity is to understand your place within that shared motion. Picture a quiet shoreline at night. The moon hangs low, silver light spilling across the water. Waves rise and fall in a slow rhythm that has repeated since long before there were names for it. Somewhere in that pattern lies the full story of gravity, the stretch between worlds, the constant exchange of motion, the invisible line connecting sea and sky. Every drop of that water feels the pull of both Earth and Moon. The difference in their strength makes the ocean breathe. You can stand there and feel nothing, yet everything is moving. The sand beneath your feet slides with the tide, the air shifts, the planet itself flexes slightly. You're part of a motion older than life. That motion never stops. It moves through the crust, the core, and the mantle. It shapes the length of the day and the spin of the moon. Even when you sleep, gravity is working, drawing you to the ground, balancing the blood in your veins, holding the atmosphere in place above you. Every heartbeat depends on that constant pull. You exist because the universe has not stopped falling inward. Look beyond the beach, and gravity connects everything else you can see. The moon circles Earth. Earth circles the sun. The sun moves around the Milky Way, pulled by the mass of billions of stars, and the galaxy itself drifts through a web of attraction that spans the observable universe. From the smallest grain of sand to the largest cluster of galaxies, all of it moves together, each part shaping the next. In that web there is no true up or down. The word down only means toward the greater mass. It's a local direction in a vast field of curved space. Somewhere else, far from Earth, another planet defines its own down, its own centre, its own tides. Every world has its own gravity, and each one's pull is a signature of its character. Gravity gives each place a rhythm. On Earth, it's the ocean's tide. On the Moon, it's the gentle fall of dust. On Jupiter, it's the compression of gas into storm bands. Everywhere, gravity turns potential into motion, and motion into pattern. It's not only a law, it's a heartbeat the universe shares. For humans, gravity is also memory. The first step you ever took as a child was a negotiation with it, learning to balance, to fall and recover. Every motion since then has been a partnership between muscle and mass. Even your sense of beauty follows gravity's lines, the curve of an arch, the sweep of a wave, the spiral of a galaxy. All obey the same mathematics. We recognize harmony in those shapes because our bodies evolved inside them. Science gives us formulas to describe these patterns, but understanding doesn't diminish the wonder. Knowing why the tides rise doesn't make them less beautiful. Understanding orbits doesn't make the moon less mysterious. The more we learn, the more we see how everything fits together. Knowledge becomes another way of feeling awe. The future of that understanding is still unfolding. We'll use gravity to explore, to travel, and to see farther than ever before. Spacecraft will surf along gravitational currents through the solar system. Observatories will map the subtle ripples of space-time from cataclysmic events. Astronauts will live under new gravities, adapting to unfamiliar pulls. Each discovery will reveal another way the universe balances motion and attraction. And yet, for all our progress, gravity keeps a kind of quiet mystery. It's everywhere, but we don't know what it truly is. We can describe its effects with extraordinary precision, yet its source remains hidden. Why space-time curves, why mass bends it, why the universe follows this rule, those are questions we still can't answer. Gravity remains both the simplest and the deepest of nature's expressions. Perhaps that's part of its beauty. It doesn't need to explain itself. It only acts. It holds planets in orbit, stars in clusters, galaxies in formation, and you, at this moment, standing or sitting somewhere under its influence. The same pull that binds the cosmos holds your atoms together. There is no separation between your weight and the structure of the universe. You are made of the same matter, obeying the same rule. The moon reminds us of that connection every night. Its gravity reaches across empty space, through vacuum and silence, to move the sea and the crust and the air. That invisible link between worlds shows how far a simple force can reach. It's not strength that makes gravity special, but persistence. It never fades completely. It never lets go. If the moon vanished tomorrow, the tides would weaken, but the pattern would continue for a while, fading slowly. The Earth would wobble, its axis less stable, its days less regular. Life would adjust, but something essential would be missing. That steady partner keeping balance. The loss would be more than physical. It would be the absence of a rhythm that shaped everything from ancient calendars to the drift of continents. So much of what feels permanent depends on gravity's constancy. The oceans, the air, the turning of the Earth all continue because this unseen thread holds. It's easy to forget that without it, nothing would cohere. Stars would never form. Atoms would never gather. The universe would remain a cold, expanding haze. Gravity gives us structure, but it also gives us meaning. To be pulled towards something, a planet, a person, an idea, is to be part of a connection larger than yourself. The pull is what keeps things from drifting apart. Every orbit, every tide, every motion says the same thing in a different language. Togetherness is the natural state of matter. The next time you look up at the moon, think of what's happening in that moment. Oceans move, rocks flex, time slows, and light bends, all in quiet harmony. You're standing inside that harmony, not outside observing it. Every breath you take is part of the same equation. You're both subject to gravity and participant in its story. Maybe that's the real meaning of down. It's not just the direction your body falls, it's a reminder of belonging. Down is toward home, toward the mass that gave you life, toward the planet that formed you from dust and light. Gravity is the feeling of connection made physical, the universe holding itself together. So when someone says gravity always pulls you down, remember the truth. It doesn't. It pulls you toward Earth, toward the moon, toward every atom that shares the same fabric of space. It's not a fall, but an embrace, one that extends from your feet to the edge of the cosmos. And if you stand still long enough, by the sea or under the stars, you might sense it. The quiet stretch between you and everything else. The steady, patient pull that has shaped all motion, all time, all life. Gravity doesn't always pull you down. It holds you in place within the endless curve of the universe. When the last light of evening fades, the moon takes its place again. Silent, steady, unhurried. Its motion is predictable, yet it never feels mechanical. The same path, the same glow, the same pull. Repeated endlessly, but never quite the same twice. That quiet persistence is gravity's language. We tend to think of space as distant and empty, but it's not. The distance between worlds is filled with unseen motion. Every particle and planet moves in response to something else. Even silence in space is motion too slow for us to feel. The line between stillness and movement, between isolation and connection, is an illusion. On a night like this, you can feel that truth most clearly, not as a thought but as presence. The moon's light falls through the atmosphere, scattering in the air you breathe. The same pull that moves oceans also tugs faintly on you. It's a link so small it escapes sensation, yet it defines your place in the universe. If you could rise above Earth and look back, you'd see how fragile and complete that connection is. The planet turns, surrounded by a thin halo of air and a single companion circling in sync. Every wave, every storm, every breath depends on that relationship. Gravity holds the pattern together without needing to announce itself. You'd also see that everything else in the sky moves the same way. The planets trace paths around the sun. The sun orbits the center of the galaxy. The galaxy drifts through intergalactic space. And all of it, every movement, is governed by the same principle. Motion responding to pull, pull guiding motion. The whole universe breathing in quiet rhythm. In the end, gravity is not about weight. It's about belonging. It doesn't push or command. It invites. It says that no object exists alone. It reminds us that every action, every orbit, every tide, every heartbeat is part of one slow, continuous gesture, the universe holding itself together through attraction. The story of gravity is also our story. Born from dust drawn together, warmed by a star's gravity, evolved in the steady pull of a planet, and now reaching outward under that same law. Every journey we make, across oceans, across planets, across time, is another expression of that single pull. We move because we are moved. So when you think of gravity, don't think only of falling. Think of connection. Think of the invisible threads that bind you to everything else. Think of the tide that lifts and returns, the orbit that circles forever, the quiet pull that never stops. Because gravity doesn't pull us down. It draws us in, into each other, into motion, into the vast geometry that holds everything in place, into the shared curve of existence that began long before us and will continue long after. And if you listen, truly listen, you can almost hear it. The low hum of a universe still moving, still falling, still together. The sound of gravity, the sound of home,